This video is about the isosceles triangle theorem. It's found in your text in section 4-4. Recall that an isosceles triangle has at least two congruent sides. So here's a question for you. What other kind of triangle on your list from section 3-4 must be an isosceles triangle? Well, since an equilateral triangle has all three sides congruent, then it has at least two congruent sides, and is therefore an isosceles triangle as well. Here's some terminology that's specific to isosceles triangles. Suppose we have two sides congruent to each other, and that's what makes it an isosceles triangle. Those two sides that are congruent are called the two legs. Now, opposite each leg of the triangle is an angle. Opposite this leg is this angle. So the two angles that are opposite the two legs are called the base angles. The side that's included between the base angles is the base of the triangle. So now we have names for all of the sides and two of the angles of an isosceles triangle. Now the remaining angle, which is not necessarily congruent to any of the other angles, is the vertex angle. And in this triangle, it's this angle right here. And now get ready. We're about to learn a new theorem that's going to be powerful in some of our proofs and calculations. The isosceles triangle theorem. If two sides of a triangle are congruent, then the opposite angles of those sides are also congruent. Okay, so in this example here, suppose that side AC is congruent to side AB. We have an isosceles triangle, and let's find the opposite angles from those two sides. Well, opposite from this side is this angle, angle C. Opposite from this side is angle B. In fact, these are the two base angles of this isosceles triangle. And the theorem is telling us that angle C is congruent to angle B. In flowchart form, we could start with a diagram marked like this, with two of the sides marked congruent. From that diagram, we could say side AC is congruent to side BC. Now, by the isosceles triangle theorem, we can conclude that angle A is congruent to angle B. Okay, here's a new word for you, a corollary. A corollary is a statement that follows logically from a postulate or theorem. It's related enough to the original postulate or theorem not to be its own new theorem with its own new name, but it's useful enough to be noted and can be cited as a reason in a proof. In other words, it's not just some random fact that can be deduced from a theorem. It's actually quite a useful fact that can be deduced from the theorem. So the isosceles triangle theorem has several corollaries. Here's the first one. An equilateral triangle is also equiangular. Try to convince yourself of this by using the isosceles triangle theorem twice. Corollary 2. An equilateral triangle has three 60-degree angles. Try to convince yourself of this by using the triangle interior angles theorem and some algebra. Finally, isosceles corollary 3. The bisector of the vertex angle of an isosceles triangle. Okay, so we have the vertex angle is angle C in this triangle because angle C is neither one of the base angles. Okay, that's the vertex angle. The bisector of the vertex angle. Okay, an angle bisector divides that angle into two congruent angles. these two angles are congruent to each other. So this theorem is telling us that this bisector, this line here, is perpendicular to the base. The base of the isosceles triangle is here. So the bisector of the vertex is perpendicular to the base at its midpoint. So we've gotten a lot of facts out of here. We've gotten the fact that this angle bisector is perpendicular. It's perpendicular to the base of the isosceles triangle, and it's not just perpendicular, but passes through the base at the base's midpoint. In other words, it divides the base into two equal parts. We'll convince ourselves of this corollary using paper in class. Now, the isosceles triangle theorem converse is also true, and I'm going to ask you to prove this as an extension problem using the hint below in green. The converse says if two angles of a triangle are congruent, so let's mark two angles congruent. Let's say angle A and angle C are congruent. Then the opposite sides of those angles, are congruent. So we're going to go opposite this angle. We have side AB. Opposite this angle is side CB. And this theorem tells us that side AB is congruent to side CB. It's just the converse of the isosceles triangle theorem. So in flowchart form, we start out with two congruent angles on the diagram. In this case, angle A is congruent to angle B. And the isosceles theorem, triangle theorem converse tells us that segment AC is congruent to segment BC. This is our deduction here. Okay, now the isosceles converse also has a corollary, just one. An equiangular triangle is also equilateral. And you can convince yourself of this by using the isosceles triangle theorem converse twice. Try it.
Hey, just laugh if you're mad. Just laugh if you're mad. Hey, just laugh if you're mad. Just laugh if you're mad.
Example 1. Find the value of x. Cite any theorems or postulates used. Okay, this diagram is marked with two sides of this triangle congruent to each other. So we know that it's an isosceles triangle with, since these two sides are congruent to each other, the third side is the base here. And the two base angles of this triangle are the angles touching the base. And since we know that those two angles are congruent by the isosceles triangle theorem, if this angle is x degrees, I can also label this angle x degrees. So I've used the isosceles triangle theorem already. Now, I can see that all three angles of this triangle are marked. So remembering that we have the sum of the interior angles of a triangle theorem, so sum of interior angles of a triangle, maybe we need to start abbreviating that theorem, tells us that x, plus, here we have 90 degrees marked, must equal 180. So x plus 90 equals 180. And therefore, we have 2x must equal 90, giving us that x equals 45 degrees. So all we've used after the sum of interior angles of a triangle is some algebra. You try one. Find the value of x. cite any theorems or postulates used.